Good morning, everyone. Welcome to the class. Let us continue the subject on power distribution network designs for high-performance digital systems. In the previous class, we was talking about the ideal PDN condition, and usually transmission line has balanced impedance 50 ohm by balancing electric field and magnetic field. However, in PDN power distribution network case of digital system, the impedance should be extremely low, like a milliohm or micro-ohm range, and very high frequencies, like gigahertz or 10 gigahertz range. But it is almost impossible to realize ideal PDN. So we have to have some practical design of power distribution network with consideration of engineering and physical design in addition to cost consideration. One possible solution of low impedance power distribution network is to put decoupling capacitors. That is the main subject of class today. Today, I'm going to give you some overall strategy to design decoupling capacitors for practical power distribution network design. I would like to remind you that decoupling capacitor is a local charge tank for switching current. Digital system is consuming a lot of switching current with very fast switching time and large amount of current. Because of that, it has very, very high frequency components as well as DC. So it has very broadband power supply network. Because of physical limitation, because we cannot put all very large low impedance decoupling capacitor in a small area, that is almost impossible. So we are going to use hierarchical design. That means we're gonna have some high frequency decoupling capacitors and mid frequency range decoupling capacitors and low frequency decoupling capacitors. And we're gonna put hierarchically, we are going to put high frequency decoupling capacitors as close as possible to the chip. And sometimes low frequency decoupling capacitors are placed on PCB with voltage regulator module. When we are placing the decoupling capacitor in a hierarchical design, we have to select decoupling capacitors who is depending on frequency range. So our decoupling capacitors will be very frequency dependent because of resonances. And we're gonna talk 3 different resonances: serial resonances, parallel resonances, and plane resonances. We're gonna have to deal with 3 different range of resonances, and each decoupling capacitor has different separate resonance frequencies. So we have to select decoupling capacitors which are very heavily depending on frequencies. Also, we have to put decoupling capacitor in a hierarchical manner in a position consideration. So some high frequency component has to be placed as close as possible to the core circuit or I/O circuit, because there is some propagation speed limit of wave from decoupling capacitors to the chip, to the circuit. If the distance between your circuit and your decoupling capacitor is far away, when we are talking about it with circuit perspective, it has large inductance. And if we consider it as an electromagnetic wave, it takes some time. Power wave, current wave will travel along the line. So we have to put high frequency decoupling capacitors as close as possible. One important things I wanted to emphasize right now is that decoupling capacitors have parasitic such as equivalent serial inductance and equivalent serial resistance. And at high frequencies, which are very important frequency range where we have to supply the switching current, parasitics are more dominant. So decoupling capacitor has very strong parasitics, and such as resistance and inductance. Those are more in considerations at a higher switching current frequencies. When we are putting many decoupling capacitors, there will be some resonances between decoupling capacitors and between interconnection inductance and interconnection capacitances. And naturally, it will happen. So we have to somehow control to avoid the overlap of frequencies of your current spectrum with these resonance frequencies. Eventually, power supply node, if you do not have proper design of power distribution network, especially decoupling capacitors, you're gonna suffer EMI problem because your power supply has voltage is fluctuating and your power supply network is becoming an antenna and it will radiate electromagnetic energy. So eventually it will interfere with sensitive systems, including RF receiver circuits, analog circuits, or sensor circuit. That should be avoided to secure the reliable operation of your circuit and system. The last effect of the power supply noise is PSIJ, power supply induced jitter. Power supply noise is transferred to I/O circuit, and it is affecting the eye diagram distortion, and eventually it will cause jitter increase. Because data jitter requirement is getting smaller and smaller, at the final minute, power supply noise and ground bounce will affect strongly on the jitter, and that is the what. So our overall, our class target is to learn about the PDN design principles, especially decoupling capacitor designs. And eventually we want to reduce the EMI level and power supply induced jitter. That is the overall picture of our previous class, and let's move a little bit deeper into the subject. In order to talk about the resonances and the frequency dependency, I would like to start to talk about electrical design of decoupling capacitors. This is a decoupling capacitor. If we are measuring the impedance of your decoupling capacitors, actually what I'm saying is that it is going to have capacitor itself. It's going to have multi-layer structures, MLCC multi-layer coffee ceramic. There are certain type of capacitors. Because to increase the capacitance, they usually have multi-layer structures. However, if they want to connect this capacitor to outside, always there is a metallic structure. Also inside the MLCC, there are vias. As far as it has metal and physical dimensions, it's going to have inductance. Usually this inductance, self-inductance, has a range of nanohenry to picohenry. And eventually I'm showing that it has to be reduced in a range of femtohenry. So it's going to have resonance. Also, because it has some metallic structure and high frequencies, the current is flowing at the surface of the metal. So it's going to have some resistance. So in the circuit diagram, it has only capacitive element, but in order to use this decoupling capacitors cleverly, we have to be able to obtain information about this equivalent serial inductance and equivalent serial resistance. You can obtain this equivalent circuit model from the measurement or from the simulations. But usually, manufacturer of decoupling capacitors are supposed to give you the data equivalent circuit model or the measurement data to you. If we look at this decoupling capacitor model in a frequency range, we can see that at the low frequencies, the impedance is dominated by capacitors because this is the impedance equation. You see that if omega is very small, this term is dominant. Because impedance is 1 over omega c. So if omega is very small, this term will be very large. So this logarithm scale will be determined by C, capacitance. And if you have larger C, you're gonna reduce the impedance lower level. So at low frequencies, if you are designing the decoupling capacitors in your power distribution network, you have to select large capacitors. But there is some problem with that because if you want to have large capacitance, your capacitor size will be large, then you're going to have larger inductance and larger resistors. If we move on to higher frequencies, J omega L will be dominant. So that means above this, at higher frequencies, omega L will be the dominant electrical element. That means your decoupling capacitor will behave as an inductor. At the cross-section of capacitance and inductance, we're going to have resonance frequency that is 1 over 2 pi root LC. So if you are having larger capacitance, if you have larger capacitance, resonance frequency will reduced. So if this is the one impedance curve, if you have larger C's, if you increase the C, then resonance frequency will be reduced. So if you wanna use these decoupling capacitors for higher frequencies, you have to use very small size capacitors. That's why it is very frequency dependent. And at the resonance frequency, will be a minimum R that is gonna be this equivalent serial resistance. At the resonance, this inductive impedance and capacitance impedance will cancel out each other. And so we're gonna have only remaining element that is resistance. So if you wanna have low, so that means that your decoupling capacitor is very efficient. Your decoupling capacitor is very, very efficient near resonance frequencies. For example, if you have 1 nanohenry parasitic inductance and you have decoupling capacitor of 1 nanofarad, roughly resonance frequency is around 100 megahertz, 10 megahertz. This is another problem associated with conventional decoupling capacitors. If our switching current has frequency spectrum over very high frequency like gigahertz or 10 gigahertz, but conventional decoupling capacitors cannot supply that fast switching current because of these resonance frequencies. If you want to increase these resonance frequencies, you have to reduce the inductance. But however, as far as you have physical size of decoupling capacitors, usually it has inductance. For example, let's assume that you have inductor, a capacitor who has the size of millimeter range, then you're gonna have 10 megahertz, the self-resonance frequencies. That means it is very effective for supplying the high frequency charge around at 100 megahertz. Unfortunately, but this may not work very well for gigahertz frequency range. That is very difficult part of our work. The only way we can reduce at this moment, you can see that only way we can reduce the impedance at a higher frequency is decreasing the inductance. So that's why I'm saying many times that inductance, number one, inductance is an object we have to fight against to design very reliable digital systems. Second one, when you are reducing the inductance, you sometimes put some capacitance, but LC resonance will be a problem, and that is the second object we have to solve. Those are the overall picture of our class. At this moment, I'm talking about I'm saying that decoupling capacitors are one solution to supply the high frequency fast switching current, and I'm explaining the equivalent circuit model. And number three, I'm giving you some limitations and challenges by the decoupling capacitor. Number one challenge is that it has self-resonance frequencies and is usually in a low frequency range. And second challenge is that we have very heavy inductance dependency at high frequencies, and we have to reduce it. One way to reduce the inductance is we have to reduce the distance, length of your interconnection. Second one is you have to increase the number of interconnections. Now, I'd like to move on to next subject to talk about one design method that is being said as multiple decoupling capacitor design. This is one way to frequently being used in conventional PCB and package design, even inside on-chip decoupling capacitor designs. Sometimes we're gonna use the same type of decoupling capacitors, and sometimes we are going to put different type capacitors. Probably we're gonna use more than 100 of same type of decoupling capacitors, and maybe we may have different 5 to 10 different type of decoupling capacitors. So I'm saying that to reduce the inductance, we have to increase the number of decoupling capacitors. By doing that, we can reduce the effect of self-resonance, self-inductance, and interconnection inductance. But all of that will take area, because we want to put more number of decoupling capacitors rather than having big one. If you put big decoupling capacitors, capacitance will increase, but inductance will also increase. So it is only effective at low frequencies, but at high frequencies, it has very high inductance. And because of that, we have high impedance. So it doesn't help. So rather than having big size decoupling capacitors, we have to put large number of small size decoupling capacitors. That is number one approach, and number two approach will be explained next on the next coming slide. But anyway, rather than having a big decoupling capacitor, we are placing small size decoupling capacitors with a large number. That means area and cost will increase. So as I mentioned many times, a signal integrity and power integrity is very expensive because nothing is free. But even though it is expensive solution, we have to cleverly use the right a solution. Now let's take a look at the effect of these multiple decoupling capacitors using the circuit diagram. So each decoupling capacitor, this line is power line in your PCB or package or on chip. This is ground line. You have decoupling capacitors here. Decoupling capacitor itself has self-inductance and self-resistance and decoupling capacitance. Rather than having a single one, we're gonna have multiple decoupling capacitors. For example, let's assume you have CPU chip, and let's assume this is package. On the back side of CPU, we usually put decoupling capacitors. And you're gonna have power plane and ground plane, and this decoupling capacitor will be connected then, and this power and ground plane will be connected to the CPU on-chip power ground network. So this amount of decoupling capacitor, usually I see that maybe 100 or 300. Now I'm trying to explain the principles and understanding why they are putting so many decoupling capacitors on the backside of package of CPU. Of course, inside CPU, they have multiple small size decoupling capacitors. Now I'd like to explain the principle by using the PDN impedance curve. X-axis is the frequency and Y-axis has an impedance. Let's assume that this curve is a case for n is equal to 1. Then it has a capacitive dominant impedance at low frequencies, and at resonance, self-resonant frequencies, it is dominated by resistance, and higher frequencies, it will be dominated by equivalent serial inductance and probably some interconnection inductance. If we put 100 of them, because of C is replaced by NC, and L is replaced by N over L. Because of this is serial connection, in circuit theory, capacitance will be added by parallel connection. Inductance will be divided by N in this parallel connection. Because this is parallel connection, we're gonna have this kind of relationship. So because of that, capacitance will be increased by N times, and inductance will be decreased by N times. But however, impedance at low frequency range is 1 over omega C, impedance will be decreased. Of course, R is also divided by N, and L is divided by N. So by placing same number of decoupling capacitance with many number, resonance frequency will not change. Resonance frequency will not change. Resonance frequency will not change. It will stay there, but overall frequencies from low frequencies to high frequencies, impedance will be lowered down. Now, I would like to emphasize number one. Okay, impedance is lower down, but still inductance is going up and going up, and we can change the bias of this impedance by certain amount, but the slope is still there. In gigahertz range, still impedance is going up and going up. There's still challenges, but anyway, from 10 to 100 megahertz range, still there are a lot of switching current frequency component because of the random nature of your I/O data, and your core computation data. So it's very efficient way. But now I told you that the number of n is in a range of 100 to 300. It doesn't go 10 to 6 or 10 to 9 because the area on the underneath of CPU is limited by a range of centimeter or 10 centimeter. And each decoupling capacitor has certain amount of size. So this may not be an eventual solution, but at certain frequency range, it is very effective design approach. So in this slide, so far I was talking about the design, one of design method where we are putting many decoupling capacitors of identical size. Now, I would like to move on to next subject, saying that we're gonna use the multiple decoupling capacitors with different types. Let's assume we are putting the decoupling capacitor with the resonance frequency 1. Let's assume this is 10 megahertz. We can put another decoupling capacitor who has maybe 100 megahertz, 200 megahertz, or 300 megahertz. So in the previous slide, we are using the same type of decoupling capacitors. Because of that, we have identical resonance frequencies. But in this case, we are having many different type of resonance frequencies. Of course, for each resonance frequencies, we can put many number of identical decoupling capacitors. If we put different type of decoupling capacitors, we're gonna have some new impedance curve like that. So that means we can make very broad low impedance curve. And bottom line of this PDN impedance will be determined by high frequency resistance, and low frequency impedance will be determined by the total capacitance, and the high frequency element will be determined by total inductance. Total means it includes the traces, ESL, and via plane, all the interconnection metallic structure will contribute to the capacitance, total capacitance, and total inductance. In this previous case of multiple decoupling capacitor design, we still have very sharp impedance, but it's gonna be go down and down to go to a milliohm range or micro-ohm range. But it is very narrow frequency approach. But as you remember that distal current has very broadband spectrum. So it's gonna have very low impedance from low frequency range to very high frequency range. This is an approach for that. But one obvious problem is that we're gonna have anti-resonances. Inductance of capacitor 1 and capacitance of capacitance 2 are meeting at this point at a resonance. And that kind of resonance is being called as anti-resonance or parallel resonances. Because of this, we're gonna generate high impedance peak. That is the cost by having these multiple decoupling capacitor designs. Because of this anti-resonance, if your current spectrum has certain frequency element that is very close to this anti-resonance frequencies, it is going to generate a huge amount of EMI and power supply induced jitter. So in conclusion, this multiple decoupling capacitor of different type helps to very broadband PDN impedance lowering. That is our acquisition by having this approach. But the cost or problem generated by this approach is the generation of parallel resonances, and it's gonna be a big issue. And still, this approach may not work very well in gigahertz range, or because it's still at high frequencies, it is going up and up again because of the inductance. Even though you have many decoupling capacitors, that is usually divided by n, having multiple decoupling capacitors, still it's gonna have inductance. Now, I'd like to discuss a little bit more about this parallel resonance. Let's assume we have a capacitor, decoupling capacitor C1, who has self-resonance frequencies, a self-inductance L, and we have another capacitor who has C2 capacitance and self-resonance self-inductance is L. So I'm saying that both inductance capacitor has the same type. That means inductance will be the same. However, I'm assuming that capacitor 1 has a larger capacitor than capacitor 2. Now, impedance curve will look like this. At low frequencies, capacitance will be dominated by C1 plus C2. And first, because of this LC is larger, L1 is larger than C2, resonance frequency 1 is smaller than resonance frequency 2. So we're gonna meet the self-resonance frequency of capacitor C1. After resonances, this capacitance inductance will be more dominant and it will move up again. And now we're gonna meet another resonance that is happening by an interaction of C2 and L. In this point, there is a parallel interaction between capacitance, inductance of L and capacitance of parallel circuit C2. That is the new resonance frequency, that is parallel resonance frequencies. Above these resonance frequencies, capacitance C2 is dominant because of L, C1 is not effective anymore. And after resonance frequency of capacitor 2, inductance, the impedance will go up. In this time, C1 and C2 are not effective anymore, or both L and L are in parallel connections, so impedance will dominate by L divided by 2. So in this simple circuit model, what I'm saying is that we're gonna generate anti-resonance frequencies. This series resonance frequency is very helpful for us to make a low impedance of power distribution network. But because of these anti-resonance frequencies, we're gonna have higher impedance, and usually this anti-resonance frequency is very source of EMI. And in this circuit diagram, I'm explaining that by considering the inductance of parallel connection with the adjacent decoupling capacitors. So if we put many decoupling capacitors of different type, we're gonna have many parallel resonance frequencies. So far, I was talking in this class. I'm talking about the basic strategy to design decoupling capacitors. Decoupling capacitor is very frequency dependent and position dependent. That is the first message I had given you. And because of that, we have also because of the physical limit to place the decoupling capacitors, we have to use the approach of hierarchical design. And with given that limitations, one clever way to design decoupling capacitor is multiple decoupling capacitors with the identical types. Rather than having big size, we're gonna have many small size, and those decoupling capacitors should have very resonance frequencies of high frequencies. Another approach is we want to make a very broad low impedance curve by using the multiple decoupling capacitor designs with different types. But however, what we found is that if we put many decoupling capacitors with the different types, we're going to generate anti-resonance frequencies, and we have to carefully control that. That is the message I wanted to give you so far in this class today. But still, I want to emphasize that at a higher frequencies, inductance is continuously increasing and impedance is increasing. This is the gigahertz range. That is where we want to send very high frequency data, especially between GPU and memory or between GPU to CPU. So we have to fight against this inductance. One way to solve that is we have to reduce the distance between your decoupling capacitors to your circuit, switching circuit. One way to do that is you have to put many decoupling capacitors inside your chip, but it takes a lot of cost. So silicon or package is package decoupling capacitors. We need more and more. And also, third approach is we have to increase the number of decoupling capacitors in this frequency range. Now, I would like to give you one example of this high frequency decoupling capacitor, and that is being said embedded decoupling capacitors. Let's assume that this is your multi-layer structure at inside chip or inside package or inside the PCB. Usually they have power plane and they have ground plane. The embedded capacitance is putting the decoupling capacitors between them. And in this case, the dielectric constant should be very high and thickness of this material should be very small and area should be very large. So that in the conventional CPU packaging, they are putting a lot of decoupling capacitors underneath. But this capacitance has self-inductance and interconnection inductance. So we want to found a capacitance which has a smaller inductance. How to do that? We are designing the decoupling capacitors inside your chip or package or PCB substrate. And you intentionally design or manufacture a PCB or package or chip who has high dielectric film between the metal and metal, and you have to make a thickness as thin as possible, probably less than a micron or less than 1,000 angstrom or something like that. Maybe nanometer scale in the future. And area should be huge. And if we put the via, in this case, we can put many vias, 1,000 vias, because this is two-dimensional. So number of via will increase significantly. By having that kind of structures, we can reduce the inductance at higher frequencies. Initial design, it has a certain inductance. By having this one, we can have this kind of lowering, inductance lowering at gigahertz range. 10 or 100 megahertz range, we can put multiple decoupling capacitors on the backside of PCB or backside of package. As shown here, we're gonna have some numerous anti-resonance frequencies, and somehow we can achieve. So ideal approach might be we are putting some capacitance and we are broadening the mid-range frequency impedance by having multiple decoupling capacitor design, and eventually we have to reduce it by a certain amount. And that is why in package area, decoupling capacitor, embedded decoupling capacitor is a good subject of research, and more will be used in the future. But still, I'm saying that in the gigahertz range, impedance is going up at a higher and higher frequencies. But slope cannot be changed, but bias point will be reduced by having more number of vias and embedded, coupled with embedded capacitors. Jun-sang, are you there? Can you talk?
네, 교수님. 안녕하세요.
Can you explain a little bit about this embedded decoupling capacitors?
그래서
조금 크게 해요.
네. 이제 앞서 말씀해 주신 디커플링 캐릭터 방안들이 두 가지가 있는데, 이제 각각에 대해서는 한 가지를 한 가지 디커플을 여러 개 놓고 나서 이제 시계 임피던스를 맞추는 방안이고, 한 가지 방안은 이제 다른 종류의 디커플을 이제 나서 전반적인 시계 임피던스를 맞추는 방안입니다. 그리고 이 임피던스, 임베디드 같은 경우에는 파워 앤드 플레이 사이에 임베디드 디스크를 깔게 되는데, 그래서 그 두께를 사업을 한 동안에 서로 거리를 간격을 좁혀주고 면적을 좀 넓게 해서 전반적인 인덕션스를 줄여주어서 하이 프리퀀시에서 인덕션스를 줄이는 방안으로 사용될 수 있습니다.
네, 좋습니다. 약간 마이크가 잘 안 들리긴 했어요.
네.
알겠습니다. 종현이 한번 설명해 볼래요?
네, 교수님. 잘 들리세요?
예, 조금만 목소리 높여서.
네, 알겠습니다. 네, 디커플링 캐paci터를 사용했을 때 임피던스가 넓은 주파 대역에서 낮아진다는 장점이 있었지만 고주파 대역에서는 꾸준히 인덕션스가 높아지는 문제가 있었습니다. 그럼 이제 이 인덕션스를 어떻게 낮출 거냐 생각을 해봤을 때 교수님께서는 슬라이드에서 말씀해 주셨듯이 인베디드 디커플링 캐paci터 획득을 함으로써 좀 인덕션스 값을 낮춰서 고주파 대역으로 더 낮은 임피던스를 유지할 수 있도록 설계를 할 수 있다라고 이해를 했습니다.
네, 고맙습니다. 그래서 지금 이제 몇 가지 그 교과서적인 티피컬하게 사용되는 이제 스트래티지를 여러분들 소개하고 있는데, 하여튼 PDN 임피던스를 납치려면 캐패시터를 많이 달아야 되는데 프리퀀시 디펜던트 하다 이런 말씀을 드리고, 그래서 이제 물탱크를 설치를 하는데 예, 주파수 대역별로 다른데, 어쨌거나 물탱크를 설치하는데 하나 큰 거 다는 것보다 작은 거 여러 개 다는 게 좋더라. 구주파로 가면. 또 인덕턴스를 줄이기 위해서 이렇게 최대한 가까이 붙이거나 셀프 인덕턴스가 작거나 비아를 많이 설치할 수 있는 이 디커플링 캐피스터가 유리하다. 그리고 이 디커플링 캐피스터 많이 왕창왕창 달다 보니까 엔티 레조넌스가 생겨서 또 다른 문제를 또 갖고 있더라 말씀을 드립니다. 그리고 영원히 그 사라지지 않는다. 임피던스가 인덕턴스 때문에 그 말씀을 드립니다. Now, I'd like to move on to the on-chip decoupling capacitor design. I mentioned many times, at low frequencies, impedance will be dominated by total capacitance, and we're gonna have some resonances. This is coming from decap resonances. It's a range of maybe 100 up to 100 megahertz. As I mentioned in the previous class, in the previous slide, we have to be careful about these anti-resonance frequencies. Also, I'm not talking very details today. We're gonna have another type resonances, and which will be covered for somehow next week, plane resonances. It is coming from the wave properties of power supply current, because there is a instant wave and deflected wave, and by combining that, we're gonna have standing wave, and because of that, also we are having resonances, and we are going to talk about that somehow little bit details later in this month. Usually it is coming from PCB, plain PCB designs, and it is coming from decap designs. As we know, because of inductive nature of decoupling capacitors and interconnections, power ground interconnection is gonna go up above gigahertz range. So the only way we can reduce the impedance in gigahertz range is putting the capacitor inside the chip. So if you have I/O switching current inside silicon, or if you have core switching current inside chip, you have to put certain amount of decoupling capacitors inside chip. By having this on-chip decoupling capacitors, impedance will change. Of course, we're gonna have resonances, and these resonances occurs by an interaction between inductance of your total power supply network and on-chip capacitance. Usually it occurs around gigahertz range. Some years ago, I had a chance to visit Qualcomm in San Diego. I think that was about 10 years ago. I saw exactly same curve, which I usually draw on my notebook, on the Qualcomm whiteboard. And they are emphasizing these resonances. In an instance, I knew that they have this problem. They have inductance of PDN, and they have on-chip decap of their application processor for Qualcomm chip. Is that Snapdragon? This frequency is about gigahertz range, and in some applications, it may interfere with RF communication systems. Anyway, why do they put on-chip decoupling capacitor? Why do we have to put on-chip decoupling capacitor? Because we have to bring it down the impedance of PDN at higher frequencies. This area is also important for noise coupling and PSIJ and EMI. But I would say some emphasis on PSIJ effect. But however, even though you have certain amount of on-chip decoupling capacitors, it has to be connected to your digital circuit. That means you have certain interconnection inside the chip. Why it has certain resistance? Because of the high frequency nature of the switching current, and inside chip the metal thickness and width is very small, so resistance is quite considerable inside chip. Because in PCB the size of interconnection is micrometer or 100 micrometer range, but inside chip it is nanometer range. So because of that, it is limited as R chip, and eventually again it is going up. Impedance is going up because of what? Because on-chip interconnection also has inductance of 500 femtohenry or 10 femtohenry, and maybe this range may be 10 gigahertz. So typically in a range of gigahertz to 10 gigahertz or 100 gigahertz, you, in addition to your this off-chip design, you have to carefully design this resonances. This is resonance by an interaction between on-chip decap and off-chip inductance and on-chip PDN lines. If you want to reduce this impedance, what you have to do is to put more capacitance and more capacitance. You have to increase the on-chip decoupling capacitance. It will take more area and it will increase the cost of your chip. Silicon is very expensive territory. And if you add more and more on-chip decoupling capacitor with more traces and more interconnections, we're gonna have more or less and less impedance curve. This is the another overview of decoupling capacitor design. 정현, can you talk?
교수님 안녕하세요.
네, 한번 온칩 디커플링 캐패시터에 대해서 한번 이야기해 보시겠습니까?
네. 이제 앞 슬라이드에서는 계속 교수님께서 그 오프칩에서 여러 개의 디캡을 연결해서 그 PDN 이제 고주파 대역에서의 그 임피던스 문제를 개선하는 방안을 설명해 주셨는데,
네.
이제 온칩으로 이제 고주파 대역으로 점점 가면서 어쩔 수 없이 계속 그 임피던스가 증가하는 경향이 있기 때문에 온칩의 디캡을 다시 배치해서 그 고주파 대역에서의 임피던스를 낮춰주는 방안을 지금 설명해 주셨습니다.
네. 근데 어떤 단점이 있죠? 온칩 디캡은?
이제 여기서 설명해 주신 것처럼 그 레조넌스가 발생하는 부분이 생긴다고
레조넌스가
말씀하셨습니다.
있고 또
네.
에어리어를 많이 차지하고
네.
비싸고.
네.
그죠? 네. Thank you.
감사합니다.
네. So Now let's take a look at a little bit about target PDN impedance. Current spectrum multiplied by impedance will be target voltage. What does that mean is that, and usually in conventional type of target network, because let's assume this is clock frequencies. Over the clock frequencies, if this is the distal and this is rising time, of course, this is one of the rising time. And above some frequencies, current spectrum will be decaying as a one over frequencies. So because of that, we can design the target impedance, which is certain, up to certain frequency is constant. Maybe it could be up to multiple of clock frequency or 1 divided by rising time. But above that, because of inductive nature, it could be increasing. So if you design your target impedance like that, combining with the switching current, your voltage switching noise spectrum will be below certain target value, because current spectrum multiplied by impedance will be your voltage spectrum. This was the conventional target PDN impedance design, and to meet this requirement, you can design these green lines. That is the typical PCB or package level design of on-chip PDN. But now, to consider noise inside chip, this may not be good enough. What I'm saying is that in these days, we have strong power supply induced jitter effect over gigahertz range up to 100 gigahertz. To suppress this PSI effect at gigahertz and 100 gigahertz range, what I'm saying is that you have to control. In the conventional design, target impedance could be this blue line, this green line, but now you have to design a new target impedance line that is controlled by PSIJ. And this impedance can be obtained by having on-chip decay plus off-chip decay. 준영이 한번 요 페이지 여기서 간단하게만 한번 내 얘기를 강조해 주시겠습니까?
네, 교수님. 그 시뮬테이니어스 스위칭 노이즈를 이제 타겟으로 해서 임피던스를 매칭할 때는 이제 고주파수에서 임피던스가 이제 계속 증가하도록 냅두는 형태로 이제
그래요.
타겟을 하지만 여기 이제 파워 서플라이 인듀스 피터를 타겟으로 하면은 고주파수에서도 임피던스를 이제 낮춰야 한다고 말씀해 주셨습니다.
그렇습니다. 그렇습니다. 그래서 그 시뮬테니어스 스위칭 노이즈가 몇 볼트 미만이다, 1mV 미만이다, 10mV 미만이다 이렇게 하면은 어차피 커런트 스펙트럼의 고주파가 줄어드니까 아까 그런 임피던스 아까 여기서 보면 이제 그 그린 라인 임피던스도 괜찮은데 IO의 지터는 굉장히 하이 프리퀀시의 영향을 받더라고요. 지터가 워낙 고주파 성분의 지터니까 그래갖고 이 온칩 디커플링 캐패시터를 충분히 달아서 고주파 여기 고주파 여기 온칩 디캡을 다는 거는 SSN을 타겟으로 하기보다는 PSIJ까지 가서 PSIJ가 주는 우리 지터 얘기 많이 했잖아요. 지터까지 보면서 이 커브를 만들어야 됩니다. 그래서 최근에 현욱이나 태인이 박사 주제가 그거와 연관되어 있는 이유가 또 있습니다. 그런 이유 중에 하나는 GPU와 DRAM과 DRAM 뭐 이렇게 CPU와 GPU 데이터 동시하는데 지터를 끝없이 줄여가야 되는데 제 개인적인 판단은 세 가지 요소가 이벤츄얼리 결정할 거다. 지터. 하나는 파워 노이즈, 지금 얘기하고 있는 두 번째는 그라운드 노이즈. 그라운드는 또 한 학기 강의가 될 거기 때문에 자세히는 하진 않고 한두 시간 하고 말겠지만 그라운드. 둘 다 제로 임피던스가 돼야 되는데 그렇지 않다는 거예요. 세 번째는 서멀이 아니겠나. 서멀 노이즈. 서멀 노이즈는 그 랜덤 노이즈로 우리가 얘기됐고 PSIJ 이런 거는 이제 디터미니스틱 지터로 이렇게 컴포넌트가 됐는데 아마 그렇지 않겠나 이렇게 생각합니다. 자, 지금까지는 지금 so far I was talking about the overall picture of the design of decoupling capacitors at PCB level and package level and on-chip level. And I wanted to give you many different several strategies: hierarchical design, frequency dependent, position dependent, multiple design, and on-chip resonances. Now I'd like to move on a little bit of resonances, but sometime I'm gonna probably sometime next week I'm gonna talk about this again. Now don't go away. I'd like to give you some measurement result. 현우, can you see this slide?
네, 교수님 잘 보입니다.
In this slide for about 10 minutes, I would like to give you some measurement result. Up to the previous slide, I was giving you lectures based on circuit diagram or imaginary PDN curves. In these days, in our laboratory, we are not doing the edge measurement anymore because we are so much confident on our modeling capabilities and accuracies of simulations over 100 gigahertz. But some years ago, about the beginning of 2000 and 2000 up to 2010, to gain belief on what we are doing, we did many measurements. And I would like to give you some example of measurement to show you what I'm saying. Please take a look at the measured impedance curve of on this solid black line. This dotted line is a case of impedance curve without decoupling capacitors. And the solid line is a case of impedance measurement with 1600 nanofarad decoupling capacitors. And we measured from 1 megahertz to 3 gigahertz. If I would repeat this again, I would extend this to 30 gigahertz. But in the first stand, you see that when we do not have decoupling capacitors, your PCB has quite high impedance, like maybe 500 milliohms. By having decoupling capacitors, we was able to reduce the impedance by this amount of, and this slope is capacitive curve. And we put 16 of them, but still it has self-inductance, because even each decoupling capacitor may have nano and inductance, but we can divide by 16. This is the inductive curve, and we have self-resonance frequencies. And the minimal point could be around 3 milliohm range that is coming from the resistance of your decoupling capacitors, divided by 16. So this is measurement verification of what I was talking in this class today. Without decoupling capacitors, impedance will be very high, but with decoupling capacitors, we was able to bring it down to milliohm range at around self-resonance frequencies. But what I'm saying is that this resonance is only around 10 megahertz. That means if you want to reduce the impedance over gigahertz range, it doesn't help. Also, we see this is another resonance frequencies. This is a resonance is generated by an interaction of decoupling capacitor inductance with PCB capacitance. PCB has multi-layer structure, so it has certain amount of capacitance. And that capacitance is interacted with the decoupling capacitors. And because of that resonance, we are generating huge anti-resonances around, probably this resonance is come around maybe 700 megahertz. And we're gonna have another resonance at around 3 gigahertz. We are going to talk, this is plane resonances about PCB power and ground plane, and we're gonna discuss it sometime next week. Again, in the previous slides, I was using the iPad. This is the micro PDF file, so I'm a little bit confused. But anyway, this is the actually a measurement result by having identical discrete decoupling capacitor with the 16 number 16. So one obvious thing is that in the gigahertz range or 100 megahertz range, inductance is dominant. And second thing is that we have to be very careful about anti-resonances. And third observation here is that our decoupling capacitor on PCB row package usually are effective around 10 megahertz or 100 megahertz. This is the measurement observation. I believe in this PCB we had a chip who has around 100 megahertz, 100 megahertz switching device. In 100 megahertz, for example, impedance is reduced quite good amount. So because of that, we was measuring the power supply noise current, and without decap, the impedance was 370 millivolts. In these days, the chip has 3.6 volt level. It was only 2000 or 2005, so it is very old measurement result, but still true is truth. And by having 1600 nanofarad decoupling capacitors, putting them, we was able to have much smaller switching noise current. At this point, what I'm saying is that you can believe me, because this 현우에게 얘기하는데요. 제가 아까까지 계속 아이패드 가지고 임피던스 얘기하고 기본 원리 설명했잖아요, 그죠?
네.
그리고
그렇습니다.
지금 이제 측정 결과를 좀 보여주고 있잖아요, 그죠?
네, 그렇습니다.
그러니까 저와 믿어지나요, 안 믿어지나요?
지금 알려주신 이론이랑 측정 결과랑 매우 유사한 걸 통해서 매우 믿을만 하다고 생각합니다.
믿습니까?
네.
네. 진짜 믿어도 됩니다. 제가 이 분야를 이제 한 20년 하면서 많은 측정과 저거를 많이 해서 다 이게 확인됐기 때문에 여기까지 이렇게 온 거고요. 그래서 요즘은 측정은 잘 안 합니다. 그냥 새로운 그러니까 물리 현상도 거의 이제 알려졌으니까 이제는 최적화를 어떻게 해볼까라는, 그래서 이제 강화학습이나 이런 걸 써보는 거고, 또 하나는 이게 이제 AI 컴퓨터라는 특정한 구조에서 한번 이런 걸 이제 이런 프린시플을 적용해서 디자인 가이드를 내보려고 하는 게 하나가 있고, 세 번째는 이게 파워 서플라이 노이즈 이슈인데 이게 시그널 인테그리티하고 연결해서 또 새로운 각도로 보려고 하는 거는 있습니다. PSIJ라고 그래가지고 옛날에는 뭐랬냐면 이런 연구가 이제 EMI과 관련되니까 자동차 급발진과 관련되는 또 연구를 많이 했고, 그래서 현대자동차하고도 일 많이 했고 우리 졸업생들이 테슬라까지 가게 된 그런 이유기는 한데, 자 어쨌거나 제가 오랜만에 이 슬라이드를 찾았는데 이렇게 돼 있더라고요. Thank you. Now this is the I think again measurement result. Please take a look at 200 megahertz case. You see that impedance, there might be this blue line is for the case of cap. Red line is 100 picofarad. Let's take a look at for these two different cases. 10 nanofarad case, we have this impedance curve, and 100 picofarad case, somehow it has high frequency resonance frequencies. And this pink line is 100 nanofarad, so resonance, anti-resonance. So depending on different decoupling capacitors, self-resonance frequency is moving higher and higher frequencies. But at this moment, at 200, let's assume you have 200 mega switching current, impedance of this blue line is higher than purple and red. Because of that, you see that impedance peak at blue line is highest, then next one is green, and that one is almost negligible. Also in the time domain, blue line has very high peaks with high frequency component. Red line, on the other hand, has more high impedance around 100 megahertz, so it has more 100 impedance frequency peaks, and it has smaller size, but it has more slowly changing. What I'm saying is, let's assume you have certain current spectrum and impedance value. Exactly this impedance has correlation with the peaks. 그러니까 이게 뭐냐면 지금까지 제가 수업에서 임피던스 높여나 낮춰라 어느 프리퀀시의 얘가 커런트와의 관계 얘기가 그대로 여기 측정해서 보여주는 거예요. 그래서 자기가 디캡을 어떤 값을 설치하냐에 따라 레조넌스가 달라지면서 특정 프리퀀시에서 임피던스가 높을 수도 있고 낮을 수도 있고 그래요. 빨간 커브는 100피코를 달면은 100메가에서는 임피던스가 큰데 200에서는 작아요. 왜냐면 셀프 레조넌스가 200에서 작거든. 그래서 오히려 빨간 100피코페럿 달면은 200메가 노이즈는 주는데 100메가 노이즈가 커지는 거예요. 왜냐? 100피코페럿 들면은 그게 주로 고주파전 잡는 데 사용되기 때문에 그렇습니다. 타임 도메인 측정에서도 그대로 200메가에서 노이즈 임피던스가 크니까 10나노페럿 다는 경우는 블루 라인은 노이즈도 크고 SSN도 크고 주파수도 고주파 성분. 근데 빨간 거 100피코를 달았더니 고주파는 잡고 100메가 노이즈가 커서 여기 100메가 노이즈가 타고 SSN이 측정이 되고 그것이 늘어지는 걸 볼 수 있어요. 주파수가 낮으니까. 그래서 이 강의에서 내용한 게 exactly 여기에 그대로 나타나는 겁니다. 현우 동감하시나요?
네, 그렇습니다.
네. 그래서 나를 믿습니까?
네, 믿고 있습니다.
네. 믿으면 같이 믿으면 어디 가죠?
천국 갑니다.
네. 처음 엔지니어링 레벨이 높을 때. 네. 그래서 제가 그래서 제가 요즘은 이 파워 인테그리티에 관심이 그렇게 높진 않아요. 하도 오래 해가지고. 근데 그래서 이제 가지치기를 자꾸 연구를 하는데 수업을 위해서 옛날 자료 이렇게 꺼내 보니까 아 진짜 다 옛날에 이런 과정을 다 거쳤구나 하는 생각이 들고요. 여기에 지금 임피던스 커브 그 다음에 타임 도메인 SSN 그거의 프리퀀시 스펙트럼 이게 3박자가 다 맞는 거죠. 예. 그렇습니다. 그리고요, 제가 이런 것도 다 했었어요. 옛날에 디커플링 캐피시터 사다가 이거 다 측정해 본 거예요. 디커플링 캐피시터 다 측정했고, 여기는 뭐냐면, we have a decoupling capacitor measurement impedance. At low frequencies, it is dominated by capacitance. At high frequency, it is dominated by inductance. And minimal the value of impedance is determined by resistance, self-resistance. But we measure two different cases. One is this one. We have only one via. Second case is another design but we have 4 vias. Of course, compared to 1 via, 4 via case inductance is smaller one. You see here, there is a little bit separation between red line. Red line has a little bit higher impedance and blue line is a little bit lower impedance. It's all depending on the number of via. This tiny difference of design will give you different impedance and resonance frequencies, and performance will be different of your system. 조세영 씨, 오늘은 마이크가 있나요? 아니면 마이크가 없나요?
네, 교수님.
오늘 어떻게 믿습니까? 조세영 씨 얘기 들으면서 오늘 끝내도록 하겠습니다. 이 그래프 한번 설명해 주시고, 그래갖고 지금 학기가 끝나가는데 보여줄 게 너무 갑자기 많이 등장하더라고요. 옛날 자료를 막 꺼내니까. 그래서 약간 지금 어떻게 마무리를 짓나 이러는데. 하여튼 요 슬라이드 설명하시면서 오늘 강의 소감 말씀하시면서 끝내겠습니다. 예.
네, 교수님. 이 슬라이드에서 설명해 주신 것들은 이제 사이먼테니어스 스위칭 노이즈가 이제 디캡의 그 용량에 따라서 어떤 특정 주파수에서 어떤 편차를 보이는지.
그러니까요.
근데
예.
그 부분에서 좀 유추할 수 있는 거는 피크점, 각 케이스에서 피크점이 이 모든 지점들이 어떤 편차를 가지는지를 확인할 수 있는 요인이다라고 말씀해 주셨고.
그렇습니다. 그리고 이게 오른쪽에 보면은 디캡을 뭘 다느냐에 따라서 직렬 공직, 병렬 공직이 막 바뀌잖아요. 그죠?
네.
그 위치에 따라서 어떤 경우는 200메가를 주로 잡고 어떤 경우는 100메가를 잡는 거예요. 노이즈를. 오늘 전체 강의를 요약해 주시겠습니까?
네, 오늘은 전체적으로 이제 디커플링 캐패시터가 어떤 식으로 구성이 됐을 때 어떤 특성을 보이고, 또 특별히 하이 프리퀀시 레인지에서 PSIJ를 고려했을 때는 어떤 부분들을 더 생각해야 되는지에 대해서 설명을 해주셨습니다. 그리고 전반적으로 설명해 주신 부분에 대해서 매우 강하게 믿고요. 잘 따라가도록 하겠습니다.
네. 내가 다음 시간에 얘기할 텐데요. 이게 인베디드 캐패시터 옛날에 만들어 봤거든요. 이거 했을 때 노이즈 얼마나 줄었냐 보면 370에서 123 줄었다. 더 하니까 10mV까지 줄였다. 뭐 이런 거 다 인덕턴스 줄인 결과는 다음에 얘기하고요. 온칩에 디커플링 캐패시터 설치했을 때 EMI 줄인 측정 결과도 옛날에 다 있더라고요. 뭐 그런 일. 그 다음에 PCB 전체를 시뮬레이션 하면 쭉 임피던스가 올라가요. 결국 인덕터만 남더라. 뭐 이런 얘기 다음 시간에 또 계속 해보겠습니다. 여러분 점점 하고 싶은 얘기가 많으면 강의를 1시간 반까지도 할 수 있겠는데 오늘 여기까지 마치겠습니다. 현우, 종현이, 준영이, 내가 네 사람 이름 보니까 현자가 되게 많네. 김자가 많고. 그래요. 오늘 수업 경청해 주셔서 고맙습니다. Have a nice day.
감사합니다.